Next speaker is Fabienne Jezequel, that we heard from Theo Mary's talk, colleagues and co-authors, and Fabienne is going to talk about benefits of stochastic arithmetic. As you can see, she's from the Sorbonne University, and I must say this is the first time we've met. We should have met before, but it's very nice to meet you.
Yes. Thank you very much for this nice introduction. I'm very happy to be here in this birthday celebration. Thank you very much for the invitation, for the organization also. So today I'm happy to present works carried out with my colleague, Steph Graya. Steph has spent a few months actually here working especially with you, Françoise. This work has also been carried out with two master students, Enzo Carlos-Martins and Maxime Spiropoulos. Thank you very much. Okay, so we want to compute polynomial roots using Newton-based methods. And so I recall here Newton method. So to compute a root of a polynomial p, you have here Newton method iterations. And if you have a single root, this method exhibits quadratic convergence. But if you have a multiple root, so with a multiplicity strictly greater than 1, you have a linear convergence. Unfortunately, we have modified Newton method. So you have the iterations which are given here. And this method exhibits a quadratic convergence when you have multiple roots. But as you can see here, M, the multiplicity is required. It must be known. So actually, we have a different approach to compute possibly multiple roots of polynomials. First, we compute the GCD of P and its derivative P prime. So we obtain a new polynomial G. Then we compute P over G, which is a polynomial that should have only single roots. And so we should be able to apply Newton method with a nice convergence rate. But actually, computing multiple polynomial roots and polynomial GCD are ill-posed problems in floating point arithmetic. And if you have a small perturbation, epsilon, it may have bad effects. So for example, in this first example here, because of epsilon, you can go from one double root to two single roots. And sometimes because of this epsilon, the GCD can have a wrong degree. And there have been several works carried out on what can be called approximate GCD, quasi-GCD. All these works are related to the computation of the exact GCD of closed polynomials, but this computation can be costful. And in this talk, we will show how to efficiently and accurately compute possibly multiple roots of polynomials, thanks to what is called stochastic arithmetic. So first, I'm going to briefly describe the principles of this discrete stochastic arithmetic. Then I will present the CADNA and the SIME library that implement it. I will show how it can be used to compute polynomial roots of, multiple polynomial roots. And then I will finish with numerical experiments carried out using the SIME library. Here I have a list of rounding error analysis tools. Of course, there are items missing, for instance, backward error computed in APAC library. So I give a few tools here. For each tool, I give the oldest reference, and they use several approaches. There is, for instance, interval arithmetic that Andreas, for instance, you know very well, which provides guaranteed bounds for each computed result. And unfortunately, the error may be overestimated. And actually, you cannot apply this interval arithmetic in a naive way in a very large code. You need specific algorithm that will tend to contract the intervals. You also have static analysis, which is a rigorous analysis that will take into account all possible input values. and it requires no execution of the user code, but unfortunately, it's not well suited to large programs. And you also have the probabilistic approach that will estimate the number of correct digits in any computed result in a code. It requires no algorithm modification and can be used in HPC codes. Okay, and so Jean Vigne has proposed the CESTAC method, which is based on such a probabilistic approach. And so with the CESTAC method, each arithmetic operation is performed several times, usually 3 times. And so for each result, you get actually, so for each operation, you get 3 results because the results are rounded up or down with the same probability. So it's stochastic rounding, a bit different from the stochastic rounding studied here in this group. And so for each result, we have 3 values, and these values can be compared. And using students' test, we can estimate the number of correct digits in the result using this formula. And so we estimate the number of correct digits using the students' test with a confidence level of 95%. And okay, there's a problem in numerical codes which are based on iterative methods. It's a problem of finding the right epsilon. So as you know, these codes usually rely on an epsilon parameter in the stopping criterion, and it may be difficult to find the right epsilon. If epsilon is too low, there's a risk of infinite loop. And if epsilon is too high, you may finish too early and not fully take benefit of the computing precision, of the working precision. And so it would be optimal to stop when the difference between 2 successive iterates is numerical noise. If we can do that, such a stopping criterion would enable us to develop new numerical algorithms where we could get rid of the epsilon parameters. And the good news is that it is possible thanks to the concept of computational zero. This concept has been introduced also by Jean Vigne. So we have a result which is computed using the CESTAC method. And what is called a computational zero is a result which is the mathematical zero. So all the values that represent the number are 0, or the result has no correct digits. So it is numerical noise. And thanks to this concept, an equality concept and new order relations that take into account rounding errors have been introduced. So we say that 2 results are stochastically equal if their difference is a computational zero. We also have a relation stochastically strictly greater than, a relation stochastically greater than or equal. And just to give an example, if we have a difference between 2 computed results, which is numerical noise, the stochastic strict relation is false, but the relation, for instance, stochastically greater than or equal is true. And so what we call discrete stochastic arithmetic is the joint use of the CESTAC method, this concept of computational zero, and the stochastic relation definitions. And with this arithmetic, operations are executed several times, usually 3 times, in a synchronous way. And so that enables one to detect numerical instabilities. So for instance, when you perform a test, you have an unstable test when the difference between the operands is numerical noise. And we can also optimize stopping criteria and avoid useless iterations that would only bring numerical noise to the solution. Okay. And so CADNA is a library that implements this discrete stochastic arithmetic, and it can be used to control rounding errors in C, C++, or Fortran codes. Actually, it provides stochastic types. So a stochastic variable consists of 3 floating point variables and 1 integer to store the accuracy. These types exist in half, single, double, and quad precision. And all operators and mathematical functions in this library are overloaded. So actually the library requires only a few modifications in user programs. So mainly you have to change the type declarations. And it can be used in parallel programs that rely on MPI, OpenMP, also on GPU codes written in CUDA and on vectorized codes. And we also have the SIME library, which implements this stochastic arithmetic in arbitrary precision. So it's based on MPFR, and it provides a new stochastic type. And again, it relies on operator overloading. And so actually we have two versions of SAM. We have a uniform precision version, and recently we have developed a mixed precision version where you can control operations that would mix several mantissa lengths. So you can control rounding errors in operations that mix, for instance, 3 variables, A, B, and C, each one having its own mantissa length. And that could be particularly interesting for accuracy estimation on FPGA, which is an accelerator where each variable can have its own mantissa length, and this length is crucial for performance. Okay, so here we have a short example. It's an expression given by Siegfried Rump that we want to compute using this SAM library. Here we compute with 122 mantissa lengths, and so here the length, and we end up with a result which has here 35 correct decimal digits. Okay, and by the way, here if we take a shorter mantissa length, we have no correct digits anymore in this expression. So now we go back to the computation of polynomial roots. So we propose stochastic version of the polynomial GCD, the polynomial Euclidean division, and Newton method that will lead to accurate computation of possibly multiple polynomial roots. So here I recall the classic Newton method. So you have the stopping criterion that relies on epsilon here. And as I said, it may be difficult to find the right epsilon. So in the stochastic version, we replace this stopping criterion using a discrete stochastic inequality, which is an optimal stopping criterion. When we stop the iterations, the digits in the last 2 iterates, which are not affected by rounding errors, are the same. And when we stop, the difference between the last 2 iterates is numerical noise, and so we will avoid useless iterations. And we take benefit of a theorem that says that if we compute using the Newton method a polynomial single root, then when we have reached the convergence zone, the digits which are common to 2 successive iterates are also in common with the exact root alpha. So what happens in stochastic arithmetic? When we stop the iterations, the digits in the last 2 iterates which are not affected errors are the same, and thanks to this theorem, are also in common with the exact root. So in the computed results, the digits which are estimated correct by DSA are those of the exact root alpha. Okay, so here we have the stochastic version of the Euclidean division. So it is a classic algorithm where we replace here the test. We use a stochastic inequality in order to discard numerical noise. We have here the stochastic version for the polynomial GCD. So again, it's a classic algorithm where in the stopping criterion, we replace the test by a stochastic inequality. And what happens, for instance, when we want to compute the GCD of P and P prime, P being a simple polynomial of degree n. Here, R2 should be null, and the return result should be R1, which is P prime of degree n minus 1. What happens in classic floating point arithmetic? Actually, R2 may have non-zero coefficients with different order of magnitude, and so it may be difficult to find a right stopping criterion. And so that leads to unexpected iterations and incorrect results. And in stochastic arithmetic, R2 coefficients are always computational zeros. And so we always return a polynomial with the correct degree. And so now we put everything together. So to compute multiple roots of polynomials, first we compute the GCD of P and its derivative P prime. We obtain a polynomial G. Yes. We compute the stochastic Euclidean division to divide P by G. We obtain a new polynomial Q of degree D. If D is less or equal than 4, then we can directly compute the roots using suitable formulas. And otherwise, we apply D times the stochastic Newton method. And one advantage here is that the polynomial Q is computed once, whatever the number of roots. And if D is greater or equal than 5, Newton method is applied to a low degree polynomial that has only single roots. And so the convergence rate should be nice here. Okay. In our numerical experiments, we have compared our results with a previous approach based on modified Newton method. So I recall here the modified Newton method iterations. And as I recall, M is required. But actually, there is a result from Jacobson that enables us to estimate the multiplicity M from 3 successive iterates of Newton method. So in the previous approach, we had an algorithm in stochastic arithmetic where first we applied Newton method to get M, the multiplicity, and also to get a first approximation of the root. And then we apply the modified Newton method in an iterative way, doubling the working precision at each iteration. And so the working precision, whatever the approach here, is always the requested accuracy multiplied by a rate, which is of course strictly greater than 1 to take into account rounding errors. We have tested the 2 approaches on several polynomials. So here we have an example of such polynomials, which has 5 roots. We have tested the approach for different degrees. We even tested for a degree 5,000 really to challenge the method. And here you have results. So obtained using the stochastic GCD and stochastic Newton method. So here you have various polynomials. Here is the number of requested digits on the roots. The number of exact digits, so the number of decimal digits in common with the exact roots. Actually, thanks to the theorem on Newton method, they are the digits estimated correct by DSA. You can notice that the number of digits actually slightly depends on the root, and the rate, which remains quite reasonable here. It's a minimum rate such that the accuracy requirement is satisfied. You also have the time to compute all the roots, and then the performance ratio with respect to the approach based on the modified Newton method. And you can see that the new approach outperforms the one based on the modified Newton method by several orders of magnitude. And actually, there are cases where the modified Newton method failed because of a lack of memory in the machine. So now we have a closer look at what happens with this modified Newton method. So we are interested, for instance, is this polynomial of degree 105. So we have to apply the method 5 times to compute the 5 roots. We have the number of requested digits, the number of exact digits, so in common with the roots, which is not the number of digits estimated correct by DSA, because here we don't have the same theorem that we had for Newton method. Here it's modified Newton method. You can see that the rate is much higher than on the previous slide. So we need a higher working precision. This working precision actually depends on the route. You can notice also a higher execution time. And as I said previously, actually the method fails for some polynomials because the necessary working precision would be really too high. And so as a conclusion, the method, the proposed algorithm efficiently and accurately computes multiple polynomial roots. And thanks to the DSA, we can discard numerical noise. We can benefit of the optimal stopping criteria, and the number of digits, which is estimated correct by DSA, is actually in common with the exact roots. There are several perspectives. It would be interesting to determine in an automatic way the optimal working precision. We could also, for polynomials having more than 5 roots, compute in parallel their roots, because actually we perform independent executions of Newton method. Here you have a few references on discrete stochastic arithmetic. You can get our papers on the computation of multiple roots of polynomials. I also give the link to the CATNA and the SIME library, and also the link to Promise, which is a library for floating point auto-tuning, which is based on CATNA. And I would like to thank you very much, and I will be happy to answer your questions.